Good afternoon everyone and welcome to my YouTube channel. So today we are looking at questions coming from the linear ladder. So the first part says that states two conditions responsible for static equilibrium. So what does it mean? So for a body to be in static equilibrium, we have to have two conditions, which is the first thing is that the sum of the torques should be equal to what? 0. The sum of the clockwise and the anti-clockwise torques should be equal to 0. The other condition is that the sum of the upwards plus the downwards force should be equal to what? 0. So if you sum or add all the forces acting upwards and the forces acting downwards, the sum should be equal to 0. So that means that we have answered the first one. So those are the conditions responsible for static equilibrium. So now, going to our main meet, which carries 10 marks, we have a 5-meter uniform ladder of weight 150 stands against a wall at an angle of 37 degrees above the horizontal as shown in the diagram. Then we are told there is no friction between the ladder at the wall, but the coefficient of static friction between the ladder and the floor is equal to 0.5. Then we are told an electrician weighing 700 newtons slowly climbs the ladder to fix a light bulb. He then senses that he is on the verge of slipping and stops at the position meters from the base of the ladder. Then we are told to calculate the value of x. So now, the first thing that we need to consider here is drawing the free body diagram. So here with me is an illustration that you can think of as the sleeping ladder. So if I am to draw this, we have something like this. So imagine this is the ladder. Now the free body diagram, we are going to say our FBD. Our free body diagram should be equal to. So the free body diagram shows us the forces that are acting on the object. So now, if you look at this, we have more like the force. We have the ladder of 5 meters. Then we have the person at x. Now we do not know where x really is. So we need now to draw the free body diagram. So how do we draw the free body diagram? So if you look at your ladder, which is this side, I have just related it. So we have the ladder like that. Then we have the force. So if you look at this ladder, it has got more like it's trying to push, it wants to enter inside. So now, this is not possible because there is a force that is acting upwards. So there is the force that is pushing more like the ruler wants to enter inside this board, but there is a force pushing up. So we are going to call this force as our normal force. So this is the force that is causing more like the ladder not to enter inside this object. Now, the other thing is that the way it is, so we have the wall here. Let me just draw like that. We have the wall there. So now, the way it is, it's like this. So as you apply more force, you will find that your ladder begins to slide. Your ladder begins to slide. Now, there is a force that is preventing this ladder from slipping or rather sliding in this direction. That force is what we call the frictional force, because frictional force opposes motion between two bodies in contact. So since the ladder is like this and it wants to slip in this direction, the frictional force should be pointing this direction. I'll call Fr as the frictional force. Now since the frictional force is pushing in this side, we are also going to have a force that is pushing against the wall. Even in the wall, this ladder is more like it wants to enter. Now imagine if this ladder, or if this wall is made of mud, you will find that the ladder will enter. Now, since it's made of wood, there is a force that is pushing against the ladder like that. So we are going to call this force as our FW like that. Then, when you look at, we have come up with that. Now, if this is 5 meters, automatically our length of this, since it's 5 meters and our ladder is uniform, meaning to say its weight is concentrated at the center. So at where 2.5 meters is, we are going to draw so from here up to here, we have a distance of 2.5 meters. Since this is half of 5 meters, so 2.5 will be here. So we are going to put our weight of the ladder, which is equal to, we are given the weight of the ladder to be 150 newtons like that. So we have this force. Now, the person also exerts a downward force on the ladder. So let's say we do not know, we are just assuming where the person could be. So we have, let's say the person is here, so the weight of the electrician should be equal to 700 newtons. Now, which length, we don't know if it's above 2.5, but we are just assuming it will be revealed later. So we have the length from the ground to where the electrician is as x. So this is our free body diagram. It shows our weight of the electrician, our weight of the ladder, then we have the weight pushing against the wall and the normal force pushing upwards. So we have come up with a free body diagram. Now when we come up with our free body diagram, let's create a diagram so we can now use our forces. So according to the static equilibrium, the sum of all the forces that are acting upwards should be equal to the sum of the forces acting downwards. So due to space, allow me to use this space. So we are going to have we can say the summation of all the forces in the y direction should be equal to what? 0. So which forces are those? So we have the normal force. So our normal force, then minus, we have the downward force, the weight of the ladder is pushing down. So minus the weight of the ladder, minus we have the weight of the electrician, which is pushing downward, should be equal to what? 0. The only thing resisting this ladder from more like entering into the object is the normal force. So we have the Fn minus the weight of the ladder we are given is 150 newtons, then minus the weight of the electrician, which is equal to 700 newtons, should be equal to what? 0. Then when we add these, since both are negative, so we can add them. So we have Fn minus 150 plus that gives us 850 newtons, should be equal to what? 0. So this means that our normal force should be equal to 850 newtons. So we have found our force acting upwards. So you will realize to say the force acting upwards is 850. Even the sum of the forces acting downwards is what? 850. So now, that is not the only force. We also have the forces that are acting in the x direction like that, or forces in the horizontal. So we can say the forces in the x should be equal to what? 0 like that. So this implies that what forces are those? So we have the frictional force minus the weight, the force on the wall. It's also in the x direction. Minus the weight on the wall should be equal to what? 0. So we are going to find that our Fr is equal to Fw. But let's just keep this equation. But we know that our frictional force is given by the formula, the coefficient of static friction times the normal force like that. So we can substitute. We know what our coefficient of static friction is. It is actually 0.5 like that, newtons. Then times our normal force. Our normal force is equal to 850 newtons. Let me grab my calculator. So when we multiply the two, we are getting a 425 newtons. So this is our Fr. So we have realized that our Fr is equal to Fw, which should be equal to 425 newtons. So we have found our Fr to be 425 newtons. So due to space, allow me to write it here just to keep it. So we have our Fw should be equal to Fr should be equal to 425 newtons like that. So having found those values, Having found those values, we can now go to our thing that will help us now find the distance, the torque. So the torque. So the way it is, this is where many people find it complicated. So this is where many people find it complicated. So you must pay attention which trigonometric ratio should you use. So here we are simply going to say, let me even erase this. So we have something like this. So how do you use the trigonometric ratios? So this is the way. So here we have the angle of 7 degrees. This means that whatever length will be here, since sine is the trigonometric ratio that has with sine, opposite, that is what you are going to use if you are looking at this side. As long as you are looking at an angle that is down here, you are going to use what? Cos, because cos is adjacent over hypotenuse. The adjacent will be where the angle is. If it is the opposite, you are going to use sine. So this is how we now deal with it. So looking at how this diagram is, so we had a 2.5 at where the weight of the ladder is, which is equal to 150. So we are going to say the sum of the torques should be equal to what? 0 like that. So now, where are these torques? So the torque is the turning effect of the what? Of the force. So as long as it's bringing the object to an anti-clockwise, we are going to assume that it's what? Positive. So this is the weight of the electrician. So we are going now to move. So we know to say this electrician is pushing the ladder downwards. So it's more like it's moving, it is causing the ladder to move in this direction. And this direction is anti-clockwise. And also the weight of the ladder is also pushing the ladder itself anti-clockwise. So we are going to add these two torques. So now we are going to have, if this is 2.5, let's consider the first one. So this ladder, the weight of the ladder is here. So what I'm going to do is I'm going to extend this line until I meet where this line touches the base of this one, or just where the two lines meet. So now, what should I do next? When I have something like that, I should look at my pivot where the force appears to act. It's here. Then, according to this line that I have drawn, I should draw another straight line, and that straight line should be parallel to the line that I have extended. Now, looking at that, you will now look at where the difference between the two. So you will look at where the pivot is to where there is this point. So since this point is the base of the angle 37, we are going to use what? Cos, because cos is adjacent over hypotenuse. So now, we are going to say our force of the ladder, which is equal to 150 newtons, then times from here up to here it's 2.5, so we are going to say 2.5 meters, then times what? We are going to use the cos of the angle 37 degrees. Why angle 37? Because this is the what? The base. We move on to the electrician. It's also causing the ladder to move anti-clockwise, so we are going to add the weight of the electrician. Take note to say torque is given by the formula force times the distance. So this distance now it is an angle of the angle 37. So now plus, what is our force that the electrician has? The force that the electrician has is 700 newtons, then times. Since this electrician, let's say I extend this line until I am here, then I also extend from the pivot point, I'm just going to have the same, then I'll look at the distance between the 2 points. So it is this base. So this base is the adjacent, or rather it is the base of this angle 37. Therefore I'm going to use the cos Now for which distance, I don't know my value of x. So I'll just say for the distance x represents the hypotenuse. For the distance x, times the cosine of the angle 37. Now, we have resolved our clockwise moments. Now, the anti-clockwise moments, if you look at the force on the wall, it's more like it's causing the ladder to move like that. So since it's causing the ladder to be like this, it is an anti, or it is a clockwise moment. So we have to subtract that minus. What is our force according to torque? Our force, which is our FW, if you remember, it was 425. So we are going to have 425 newtons times the distance. So we are going to use the same approach. So we have, let me wrap this. So we have the force of the wall on the wall is pushing forward, as you have seen. Then what I'm going to do is every time I was drawing a line parallel to the other. If you remember, when I drew down, I also drew another parallel line. Two lines that will never meet. So I will also have to draw a parallel line like that. Then I will look at the distance between where the pivot is to where that line is meeting. So we have this distance, which is the same as this distance. Now this distance is opposite to this angle, and we cannot use cos. So we are going to use what? Sine, since sine is opposite over hypotenuse. So I'm going to say times the times the length of the ladder, which we were given is 5 meters. So 5 times the sine of the angle 37 degrees should be equal to what? 0. The sum of the torque should be equal to what? 0. That's what we said. So let us now do our calculation. So we have 150 by 2.5 cosine of 37. We have a 299.488 plus this one. We have the weight of the electrician, 700 by the cosine of 37. So we have plus a 559.0448. Then we have x. Then minus, we add this, or we subtract that. We have 425 by 5 sine of 37. We have 1,228.886 should be equal to what? 0. Then we have this one and this one alike things. So we have 559.0448. Then when we subtract this and this, we are getting minus 299.488, since they are of different signs. So we are getting minus 979.37 should be equal to 0. So this will go the other side. So we have 559.0448. X should be equal to, taking this side, it will become positive 0.3689. So we divide over 559.0448 over 559.0448. So when we divide this, we are getting our x to be equal to, divide by 559.0448. So we have a 1.752 meters. So that is how we can find answers to such a question. So thank you very much for watching my video, and I hope you would like, subscribe, and share for more. Thank you very much.